So thank you very much that I can present today about fifth generation district heating and cooling networks. My name is Marco Wirtz. I worked 6 years at RWTH Aachen University, and right now I work for a spin-off of RWTH Aachen University, nPro. And yeah, I'm happy that I can present today in remote because I couldn't make it to Spain because of the strike in Germany. But yeah, I can still present my ideas today. That's great. Let me start. What's nPro and what did I do in the past? Maybe one slide just to show that. nPro is like I said, a spin-off of RWTH Aachen University, and we offer different services, also with focus on fifth generation district heating and cooling networks. We were founded last year. Yeah, we develop a planning tool because it's pretty important that you have tools available for engineers who can design their districts with these software tools. And you can, for example, plan a fifth generation district heating and cooling network with it. And what we also offer are design studies and planning services for those systems. And I'm actually also a PhD candidate at RWTH Aachen University. So I worked 6 years. Wait, this slide. I worked 6 years in this field of fifth generation district heating and cooling networks, and did quite a bit of research in this field. So I will stick with the term fifth generation. Also, Thermonet is also a nice name, but I want to break my tongue today. So I will say a fifth generation district heating and cooling networks. This slide is familiar. We saw it already a couple of times today. So what is a fifth generation network? So from my perspective, the main difference to a normal district heating network is that we have the decentral heat pumps in every building. And we have this network which is at an ambient temperature. That's the main difference to a normal district heating network. And then, yeah, we have a central heat source that can be anything like we heard before. The classic heat source is the geothermal field that we can use. And what is also special about it, we heard it also before, is that we have a strong coupling with the electricity grid. So because we have heat pumps in every building, we need a good infrastructure for electricity as well. And yeah, we can also utilize a lot of photovoltaic, of course, if we have it available, because on the building roofs, we can directly use the photovoltaic electricity inside the building for our heat pump. All right, that's a basic concept. We saw it already a bit, and we also heard quite a bit about the different generations and this and the discussions in the academic world about the generations. I put this slide here on to show what's about these generations. So there's from Denmark, basically from the academic world, there's this definition about the different generations from first to fifth generation. And the first generation was really, in the past, where we built steam networks, which very high temperatures, like up to 200 degrees Celsius, and we distributed very steam to the buildings. That was very inefficient because we had very high losses due to the high temperatures. And then the second and the third generation was, I would say state of the art, which is built in Europe quite often, and which is in operation right now in many cities, where we distribute still very hot water above 100 degrees Celsius in many cases. And this comes from then burning fossil fuels, normally with CHP units or with boilers. Problem is that we still have pretty high losses, of course, due to the high temperatures, and that we can't really use the new heat sources like ambient heat sources for these technologies, because we can't push the temperature to 100 degrees Celsius with a heat pump. That's very inefficient. So we have this trend towards lower temperatures, and the innovative concept is the fourth generation, also defined from researchers in Denmark. And they say, okay, we have low temperatures like 50, 60, 70 degrees Celsius, then we can use new technologies, new heat sources like geothermal, solar thermal, and so on, which gives us an opportunity to realize fully sustainable energy networks. And yeah, this jump to the 5th generation is pretty recent, actually. It's not, it's pretty new, this technology. I would say like a couple of years, we are starting to build these systems. And there we have this trend to even lower temperatures. So we are talking about between -5 degrees to 20 degrees Celsius in many cases. There's a big difference between both concepts in terms of temperature. The efficiency can be higher, but it really depends on the use case. If you want to build a 5th generation district heating network, or maybe you want to build a 4th generation district heating network. So we can utilize many different heat sources. I will explain this a little bit later. And we can provide cooling, which we already heard is a big advantage of that. Some key advantages just on one slide, and then I will go through it a bit and talk about it in detail. Of course, we can integrate, like I said, low temperature heat sources, so rivers, lakes, and so on, geothermal, of course. That's a big plus of these networks. Then we can provide heating and cooling with the same infrastructure. So if we have the network for heating, then we can directly use it also for cooling. That's very low cost, very low operational costs, also to provide cooling in summer with it. We have this waste heat recovery effect. So we can reuse heat from a building that has a cooling demand in buildings that has a heating demand. I will explain this on the next slide. Then what we also heard is we have low heat losses, in some cases even no heat losses at all. And what we saw in the previous presentation, we have actually heat gains. So we can use the network as an asset and use it to collect heat. That allows us also to use the plastic pipes, which are obviously cheaper than the steel pipes with insulation around and easier to install. And one key advantage is also that that not every building really needs its own heat source. The building owner, not every building owner has to think, okay, how can I decarbonize my building? What can I do? Which funding is there? Which technology should I use? But we can actually solve the problem a bit more on the district level and organize one solution for a whole district and have one central heat source like a geothermal field, and then offer the building owners, hey, we have the solution here, you can connect to our network, and then you can decarbonize your building without much thinking, planning, and so on. So that's also kind of comfort, as we heard it before. And then the last advantage, or one of the advantages, is that this network allows the buildings to actually take the temperature that it actually needs. So if we imagine we have a district with many buildings, different buildings, like maybe modern buildings, which need a low temperature, and also old buildings, which may need a higher temperature for heating, then this network allows that we just distribute this low temperature to every building, and the heat pumps inside the buildings really increase then the temperature to the level that the building actually needs. So if it's a modern building, we don't have to raise the temperature too much. We only need maybe 35 degrees Celsius. And if we have an old building, then we need to increase the temperature to a higher level. But we don't have to provide a high temperature to every building, but we can actually increase the temperature individually for every building. That's also a plus for these networks. I want to explain this waste heat recovery effect a bit more in detail to show what's the advantage here. We see here the 5th generation district heating network with the low temperatures, a warm pipe and a cold pipe here in red and in blue. And we have two buildings connected to it. and we have the decentral heat pumps to supply the heat demand in the building. We can cool the building. We may need a chiller, but this could also be like just a heat exchanger if the temperature of the network is low enough. And then we have two effects that we can use. For example, we see it in office buildings sometimes, that the office building has heating and a cooling demand at the same time. So maybe the sun is on the south facade, and we have a cooling demand in the south, and we may have a heating demand in the north. Then we have both demands at the same time. It could be also that we have a domestic hot water demand in the building, and that's the reason why we have heating and cooling demands at the same time. So a few scenarios can be thinkable. And then we can use the waste heat from the cooling application directly for the heat pump in the building, and we don't need any further energy from the network. So that's the first effect in such a network, that we can directly balance heating and cooling demands within a building. And the second effect is then that we can also balance heating and cooling demands between buildings. So if we have buildings with different usage types, for example, maybe the right building is a data center, or maybe a public swimming pool or whatever, and we have too much cooling demand in there, then we can use the waste heat and feed it into the network. And another building which may need heat can then use it as a heat source for covering its heating demand. So that's the second effect, so balancing between two buildings. And this means that the load at the central heat source, like a geothermal field, decreases, and that we need less borehole meters, for example, or just less heat sources. During my PhD, I made a survey for fifth generation district heating and cooling networks in Germany, where I collected a lot of data from different municipalities and engineering offices. I want to show a few these survey data that I collected. It's available in a paper here. And I found that we have about 100 fifth generation district heating and cooling networks in Germany. I could collect data for 53 of these networks. And I also saw that the first network was actually built in 1981. So not that new, actually, the technology. So it was a pretty small district, which was supplied by a central geothermal heat source with decentral heat pumps. And yeah, as you see in this graph here, in this diagram, it's pretty increasing very quickly, the numbers of installations and the number of projects. So the technology is really in the last 10 years, yeah, accelerating very, very strongly. I collected all this data from the different districts, and on this map you can see the overview of fifth generation district heating and cooling networks in Germany. I think even a few more than the 53 ones. And what you can see here is also the heat source that the networks use. So the dark green circles are geothermal collectors, so shallow geothermal energy, and geothermal probes, geothermal boreholes are the light green ones. And we can see that many of the projects actually have geothermal as the main heat source. Some others are using ground and well water, the blue ones here. And often we can also see that ambient air is also, in addition, often a heat source that is used in these networks. Yeah, some rely still on fossil fuels, for example, for backup units. Some use solar thermal, but that's not so common, solar thermal in fifth generation, because the temperature is just too high and it doesn't make sense to produce high temperature heat for a fifth generation district heating and cooling network. If we have waste heat, of course, that's always an option. There are a couple of districts which use waste heat from industrial sites, for example, to put it into a fifth generation heat network. And sewage water, we heard it before, is a very good option. Actually, we have a lot of potential also in Germany, in the cities especially, where we can use sewage water. But it's not that often used until now, but I think in the future, it will increase a lot. And ice storages, that's maybe a not so common usage, but we have a couple of projects also where we use ice storages, which are buried in the ground as a heat source. I want to focus in this talk about the geothermal energy aspect. And we see here the overview with the different heat sources. So like I said, many of them, that's the blue and the red one, use geothermal heat sources, geothermal collectors and boreholes as the main heat source. And yeah, the capacity of the central heat source ranges between pretty small networks like 50 kilowatt as a central heat source to 43 megawatt. In Berlin, there's one fifth generation network planned, which will be very large and will have many different heat sources. And in total, it will be 43 megawatt. So yeah, as I said, geothermal energy. So we have 3 different kinds of geothermal energy. What is normally used are the shallow geothermal energies, not so much the deep geothermal energy. That's like more high temperature and more investment. We normally use the shallow geothermal energy for it. I think the classic one are the boreholes, but I want also to show some examples where we use a very shallow geothermal energy as a heat source for these networks. Yeah, that's how it looks like, obviously, when you install a borehole field. Some of the advantages that are connected to these shallow geothermal applications were already mentioned. One advantage is that we have a central heat source, and that means also lower investment costs, because not every building needs its own heat source, but we can install it at one place with one some machinery and so on, with lower investments. And the other effect that we also heard in the previous presentation, the diversity effect, which means that we can install less borehole meters for the same number of buildings compared to individual boreholes for every building, just because we have the effect that not every building has its peak demand at the same time. So that these are 2 effects: lower investments and the diversity effect, which comes from the central heat source aspect. How does it look like? A couple of projects, innovative projects in Germany, use these collectors here, these horizontal collectors. So they are not so much in the ground, maybe 1 meter, 150 something. And then we have either these plastic pipes, which we just put into the ground, which is low cost and very easy to install. But there can also be these solutions where we have this prefabricated plastic pipe elements, which we put into the ground and takes the heat from there. And normally you find like space enough to install these things next to a district, for example, and takes the heat directly from there. It's another picture where this is installed, these prefabricated elements. You just connect them to such a collector pipe, and then you can use it as a central heat source for the geothermal, for the 5th generation network. Of course, these elements and these plastic pipes and so on, they are very low cost, so very low investments are needed. It's very easy to install. You don't need so much effort to do it, and you just need less workforce also, because it's just standardized kind of, and it's not so much investment that you need from a workforce perspective, but also from investment perspective. Another idea which comes up in a couple of projects in Germany, they want to use so-called agrothermal collectors. So that means that you use basically the land of a farmer to install these collector fields. And here on the right, you see such a machine which puts these plastic pipes into the ground, so it goes over the land and then places the plastic pipes into the ground in 152 meters depth. I want to also show a couple of other options to provide, or which can be used as the heat source for fifth generation heat network. If you have a sea close by, that's not so often in Germany, but for example, Barcelona would be a good place, but also other cities in Scandinavia, for example, use it. Then you can use a sea directly as a heat source, even if it's a low temperature a heat source, then you can still use it because you can distribute the water from the sea directly in the city. Like if it's 6 degrees, maybe 10 degrees Celsius, you can distribute it, circulate it in the city, and connect the buildings to it, and the buildings take the heat that they need for heating. Or in summer, they can use it also for cooling. So you have one infrastructure if you install it for heating and cooling. That's the main advantage. There's one example project, for example, in Norway, where they use the seawater and also provide free cooling. Another project is, I think, in planning in Marseille, in France, and also in Germany. We have a large lake in the south, the so-called Bodensee, and there we have a couple of studies who want to check if it makes sense to take water from the sea or from the lake and distribute it in the city, circulate in the city, and use it as a fifth generation district heating network. Another option are, of course, river and lake water. As I said before, in Germany we have a couple of rivers that we can use for that. And there were also studies where they checked, okay, how many inhabitants actually live close to a river in Germany, so in a distance of 1 kilometer, 2 kilometer, and so on. That's quite a high share, so it's not so common to use it right now, but it has a very high potential for fifth generation district heating and cooling networks. If you can actually use these potential to as a heat source for these networks. Another example as a heat source that we use in Germany are old coal mines. We have a couple of them. I'm not sure about Catalonia, but in Germany we have a couple of them where actually warm water comes up from the ground, and it's basically for free. And we can directly use it as a heat source for fourth generation maybe, or for fifth generation district heating and cooling network, and heat buildings close by. So there are also a couple of projects which are currently realized. Yeah, one slide about the network temperatures. I said it already, the typical temperature for fifth generation is between -5 and 20 degrees Celsius. And that was also coming from my study, from the data. So most of the projects have this temperature. And we see here most of the projects have around 8 degrees Celsius. So that's the temperature for geothermal heat sources. That's the most common way, or most common temperature actually. Yeah, I want to show a few pictures about the plastic pipes that we use for these networks. You can see it here on the left, where we install these things in the district. So we don't have these heavy steel pipes with insulation, but pretty lighter plastic pipes. And it's much easier to install, of course. We don't need any welding and so on. And yeah, you can actually use it as a heat collector, which I put on this slide. So what we already heard, that we have low losses because of the low temperatures. If we have like 5 degrees Celsius inside the pipe, then we don't have any heat losses. And if we have very low temperatures in the winter, maybe 0 or 2 or 3 degrees Celsius, then we have quite some heat gains that we already heard in the presentation before, up to 25% I heard. So that's quite a large amount that we can take from the network itself as a heat source, so to say. So that's one advantage. Most of the networks in Germany use these uninsulated plastic pipes. And what I also wanted to mention that most of the networks are pretty small in Germany right now. So 60% of the data that I collected were the networks were below 2 kilometers in length, but it's currently increasing. So the new projects, like the project in Berlin, has a length of 12 kilometers. And I think as the technology becomes more widespread, the length of the networks will also increase. Currently, most of the networks are built for new build districts. So 43 of the 53 districts are new build, but as I think in the future it will go into the existing building stock also, because it's there's no problem to install a 5th generation district heating and cooling network for existing districts as well. One last slide about the cooling aspect. I think for Barcelona or Spain in general, it's more important than for Germany, but still in Germany, we are talking more about cooling because we have this heat periods in summer which become more frequent and more pronounced. And we also have something like heat island effect. So the cities are pretty warm in summer especially, and we need cooling there to ensure minimum comfort. And that's a very good application then for 5th generation district heating and cooling networks. If we don't want to look our cities like this, then we can try to provide it from a central heat source or cooling source, and don't have these decentral chillers in every window. And it's low cost. In the study that I made, 11 of the 53 districts, they just provided the cooling for free, so no additional costs for the user, and that makes it very attractive, of course. One last slide. I just thought about, okay, Spain is maybe a bit different to Germany, but there are a couple of advantages if you want to employ this technology of 5th generation district heating and cooling networks. In Germany, we have less photovoltaic yield for every kilowatt peaks that we install. In Spain, we have more photovoltaic, of course. And that's also a very important point if you want to install a 5th generation district heating and cooling network, because you can directly use the electricity from the PV for the decentral heat pumps. That's a good combination, of course. And you also have heating and cooling loads. Cooling loads probably more than in Germany, and maybe even balanced here. I'm not totally sure, but quite an overlap of heating and cooling loads, and that makes it also very attractive for 5th generation district heating and cooling networks. Shallow geothermal energy, I think it's available everywhere, more or less. We can use it everywhere, and the combination of it, is pretty promising for this technology. The heating and cooling aspects, which are both very high, the photovoltaic yield, which is high, and also the geothermal. If you use it with a geothermal heat source, then you get a pretty promising combination, I think, in this area for such a technology. All right, that was it. Thank you very much for your attention. I hope you got some ideas from it, and I think afterwards there will be a question section.